So welcome everyone to this Engineering Research Symposium presentation. This is part of a series of online presentations that highlight some of the excellent work being done by our research partners using our technologies. I'm very pleased today to be joined by Chen Tang from the University of Waterloo, who will be presenting on the MapleCar as part of this series. Now, before we go on, I just want to provide a quick introduction to MapleSoft and why we provide support for projects like this. So MapleSoft has over 30 years' experience in supporting advanced research projects. In fact, the company's core symbolic technology, which is the ability to allow computers to handle problems at the equation level instead of attempting to solve them purely numerically, that was developed as part of a research project in 1980 at the University of Waterloo in Ontario. So since then, many of our highly advanced computational technologies for solving complex analytical problems have had their beginnings in many of these research projects. So MapleSoft was founded in 1988 to commercialize these technologies.
Everyone, my name is Rochelle Angel, and I'll be your host for today's webinar, a MapleSim e-symposium series, Meet the MapleCar, a new topology-based simulation tool in vehicle modeling and control. I'm joined here today with Chen Tang, who is a graduate student of the University of Waterloo, and Graham Jackson, who's an engineering specialist here at MapleSoft. Before we get started, please note that you can use the chat window to contact me for help if you encounter any technical glitches during the webinar. You can access that window by clicking on the chat icon in the top right corner of the screen. If you're in full screen mode, then you will need to navigate your cursor to the top of the screen to expand the WebEx toolbar to see the chat icon. Now, I'll pass the floor to Graham so he can begin today's webinar. Enjoy, everyone.
Thanks, Rochelle. So welcome everyone to this Engineering Research Symposium presentation. This is part of a series of online presentations that highlight some of the excellent work being done by our research partners using our technologies. I'm very pleased today to be joined by Chen Tang from the University of Waterloo, who will be presenting on the MapleCar as part of this series. Now, before we go on, I just want to provide a quick introduction to MapleSoft and why we provide support for projects like this. So MapleSoft has over 30 years' experience in supporting advanced research projects. In fact, the company's core symbolic technology, which is the ability to allow computers to handle problems at the equation level instead of attempting to solve them purely numerically, that was developed as part of a research project in 1980 at the University of Waterloo in Ontario. So since then, many of our highly advanced computational technologies for solving complex analytical problems have had their beginnings in many of these research projects. So MapleSoft was founded in 1988 to commercialize these technologies research projects. So MapleSoft was founded in 1988 to commercialize these technologies through the development of the popular mathematics tool Maple and the powerful multi-domain and engineering simulation tool MapleSim. Now we're a leading provider of high-performance tools and technologies for solving a myriad of technical problems in engineering, science, and applied mathematics all throughout the world now. Our software and services touches hundreds of thousands of people working worldwide and are well known for our expertise in mathematical and system-level modeling analysis. So we acknowledge that we can only advance through the support of engineering projects that require our technologies and have been recognized as a powerful partner in these endeavors. Specifically, we can provide guidance and support in the development of research proposals through in-kind and technology contributions, as well as helping to foster relationships with other industrial partners. Furthermore, we can provide help in skills development of your team members through training and application development support, as well as providing openings for co-op placements and internships. So lastly, we recognize that working with our research partners provides a very rich seam of talent that is much needed by ourselves and other industrial partners. Consequently, we've tried and we have hired many engineers to work within our development and support groups and opened up opportunities for new hires within our customers and partners. So with all of that in mind, let me introduce you to our guest presenter today, Chen Tang. Chen is a graduate student at the University of Waterloo, and he's presenting his work, which was originally shown at the North American Modelica Users Group Conference in 2016. Thanks for joining us today, Chen, and I'll pass it over to you for your presentation.
Thanks, everyone. So today I'm going to present the MapleCar, so a new topology-based simulation tool that we propose for vehicle modeling and control. So to begin with, as we are proposing some vehicle dynamics and simulation control tools, so let's first have a quick look at what are the standards that we think of as a good, say, vehicle dynamic simulation control tool. So we think of the following criteria. So first, it should have an easy and intuitive using interface. It has predefined vehicle subsystem models, templates, database, driver models, virtual proving ground, and vehicle control tools, and even multidiscipline support and handling-in-the-loop connectivity. So with this in mind, then we look at the existing solutions on market and identify that, yes, they're doing pretty good in some of the areas, but there are still some of the areas that we might have a chance to improve them. So for example, when we look at the easy and intuitive user interface, and we notice that some of the most general purpose based on multibody-based mechanical system modeling tool, they are, to me, intuitive to be used because all the linkages, joints you modeled you can see them exactly on the user interface. But at the same time, this intuitive came at the cost of losing the easy to do the modeling. For example, especially for vehicle applications, if you start from scratch, you're going to build, say, suspension systems. You need to start from all the hard points to the linkages and to all the various joint connections. So that's definitely not so easy to be used. And at the same time, especially for vehicle dynamics and control, we have some, say, reduced order modeling tools, right? Basically, the idea is based on some the characteristic curves or data which are extracted from experiments, and later on we use this for simulation. So in this way, it's straightforward and easy because you don't need to know the implementation details. But it came up with the problem of losing the intuitive, right? Because most of the time people don't know what those characteristic curves means, and in some cases they even need to use specialized tools to get those characteristic curves. So that's something we see. There seems to be a chance to provide a scalable subsystems without increasing the complexity. So by scalable, we mean sometimes it can go to the full detailed modeling, right? And while the other times, if needed, it can also switch to those characteristic curve-based modeling, which make the modeling much easier. So we find topology-based modeling could be a best solution to address these problems, which we'll present later. And also we noticed that the existing solutions, which mainly based on, say, mechanical simulation, in many cases they lack the multidiscipline support, and it's a little bit tricky to implement the control tools in the simulation environment. Usually they need to, access to third-party softwares to do code simulation, to implement the user-specific components or specific algorithms. So that brings the chance to have an integrated environment for controller and multidiscipline system development. And we found Modelica-based platform could be a good solution to all those problems. So I would like to begin with this topology-based modeling. So just keep in mind, so we are focused in, say, vehicle system modeling. So we first identified that vehicle is made of subsystems with fixed topologies. So if you look at the left bottom screen of the picture, so you notice that that's some common, say, topology connection of the vehicle subsystems. Let's start from the driver. So driver always sends some signals. Topologically. If you think it topologically, driver always sends some signal to the power control units, to the steering systems, to the braking systems, and all these systems will work with other subsystems. For example, the power source unit, transmission systems, suspension systems, and all the the forces, torques will always finally end up with some changes on the wheel. Some changes on the wheel state, and then finally via the wheel road interface, some force is going to be generated. Finally, change the dynamic reaction of the systems, and then driver, by looking at the feedback states and then do the comparison and then do a better control to coordinate, then just to close the control loop to again send signal to the power plant to the steering system, and to the braking system. So that's what we mean by some fixed topology connections exist in vehicle subsystems. And we realize that, and if in simulation, we can replace each subsystems by using a simulation block, which later on we'll refer to as SuperBlock, and we implement them. So that's what you see on the right lower of the screen. So that's the implementation of the MapleCar package. So each block stands for each subsystems in the real world, and we just connect them as the topology connection in the physical world. So this way, we believe it's more intuitive to do vehicle simulation, to do vehicle modeling, connection, and simulation. And later on, you will see that by incorporating some advanced, say, language features provided by Modelica, we can easily switch the type from type, changing, say, parameters, and define the sensing and output. All those features are available with these topology-based features. Then next slide shows how Modelica came into the picture. So with Modelica, we notice the modeling of dynamic behavior of technical systems, especially with various domains, can be modeled in a very convenient way. That's actually why we choose the platform to implement our idea for these super components, vehicle topology component-based vehicle modeling. And during the development, we noticed that MapleSim is a strong Modelica-based tool with available toolbox especially for vehicle applications, because we noticed they have a long list of driveline components, verified battery components, and tire force components already predefined. So later on, you will see we integrate them and put them into the package, and it will be very easy and efficient to do the vehicle modeling. So that's why we use Modelica-based platform for our proposed solutions. Then came the problem, how we are going to redevelop the MapleSim, which is a high-performance multi-domain physical modeling and simulation tool, to a specialized tool called MapleCar for vehicle dynamic simulation applications. So as mentioned, MapleSim has already have some vehicle subsystems already defined. So we identify those predefined components and extending the vehicle subsystem library. For example, the chassis systems, the suspension systems, wheel modules, all those stuff we need to do the vehicle mechanical modeling. And then by combining these vehicle subsystems, so we should be ready to do a full vehicle simulation. So that's the traditional approach, those multi-body approach for vehicle simulation and analysis. And later on, we also noticed that if we can incorporate or have some built-in test rigs to analyze the detailed, say, multi-body components, for example, suspension, we have some test rigs to analyze the suspension performance and then extract some curves and data, and later on we can use these characteristic curves and data to do the reduced modeling. So that's the other approach we suggested to do the vehicle modeling in MapleCar package. And noticing that, we also realized that having the vehicle subsystem alone ready is not complete. We also need, for example, the driver models, virtual proving ground, and all other tools to support full vehicle model to work in conjunction with, mechanical model to do full vehicle simulation. So that's the suggested approach that we go from MapleSim to our proposed MapleCar package. Then this slide shows you some of the subsystems we defined according to the topology connections, and we implement them in our MapleCar package. So you'll see we have the suspension, tire, corner module, axle module, steering, anti-roll bar, braking systems, body or chassis systems, powertrain, environment, control, or driver. So all these subsystems are identified and implemented in our MapleCar package. Then this slide shows you that, so each block you see in the previous slides is what we define as a super component. So what the super component can give us, so with each super component, you will be able to select the subsystem type. So on the right screen, you will see that's the user interface for wheel definition. So when do modeling, so user don't need to care about the specific type of the tire model to be used. So they just need to put a general SuperBlock in the user workspace, and later on they can select the type, just like specifying the parameters. So that's one of the key features by using with super components. And also later on, you'll see you can easily modify the system parameters. The picture shown here is actually the specific tire parameters for Fiella tire models. Later on, you'll see if we switch to other tire models, say linear tire models, so these parameter input blocks will go away and be replaced by the specific input blocks to waiting user to key in the numbers for the linear tire models. So that's some benefits we can have by using with this super component idea. And we also will be able to configure the connection frames and do the same thing. I specify what are the output readouts for the specific model. So that's all the things we can do with such super components. Then this slide showed you the language details because we use the Modelica. So I showed you some of the demo code how we are going to implement the super component idea. So we still use the wheel module as an example. So first, we begin with defining some interfaces by using partial model feature, language feature in the Modelica. And then later on, we implement all the detailed specific implementation of various types of tire force models. As you see, the Fiella, linear, and particular models here. So they always extend the predefined interface. So by doing this, having the interface and each standalone subsystem ready, so later on we can create some kind of container-like, we call it wheel super components. So we are going to extend the interface, and so it can be initialized at runtime for various detailed concrete models, say in this case, either Fiella, linear, or particular models. So that's some kind of language features that we use from Modelica language to support our implementation of this super component idea. And with the super components, so the workflow, suggested workflow of vehicle modeling should be something like this. So first we identify the components, we first identify the subsystems we need for the specific vehicle modeling tasks. So in this example I've shown you, so we just need a frame body with suspensions, wheels, and a steering mechanism. So we just drag and drop them from the existing, later on you will see the MapleCar library. So we don't need to worry about their specific, say, types, connections at this stage. So we just drop in the modules and do the topology connections. And then we go to the next step. So we are going to specify those parameters. So then you need to think about what the specific tire model to be used, what the suspension types. So, but thanks to the super component idea, so types themselves is a parameter. So we can firstly define the specific type and then key in the numbers, the parameters along, for that specific type. Then we define the full vehicle model in that way. So to sum up, so we always came up with some kind of generic collection of blocks and then keying the specific parameters to finish the full vehicle modeling. And later on you will see we, with some advanced tools, in collaboration with Maple, we can easily, even make this modeling process even more simpler by, again, identifying the fixed topology in vehicle systems. We can always end up with some vehicle systems like this, and a driver model and an environment model. So we do the connection in between, and then the model should be ready for solving. So after solving, you expect to see some of the predefined post-processing results. So I've shown some of them here. You will see the trajectory of the vehicle, some suspension bumps, and also some wheel spin rates readouts, and even the animation readouts. So that's the workflow from thinking about the topology of the vehicle, then define the parameters, define the types, and then assemble the model and do the vehicle modeling, simulation and post-processing. That's the suggested workflow. Okay, so from here I'm going to switch to the MapleSim window and to have you a better idea about post package look like? Okay, so here's the MapleSim window. So you will see on the left panel, you will see various libraries shipped with the MapleSim package. So you will find the signal blocks, electrical, mechanical, and multibody, which we'll use a lot in vehicle-specific, mechanical modeling, detailed high-fidelity modeling. And also you'll have those multi-domain supports, for example, the hydraulics, the thermal, the magnetics, battery. And these three blocks is, I would say that's some kind of vehicle-specific libraries. They have some battery libraries for vehicles, drive lines, and even tire force models. So that's what, provided by the MapleSim environment. So what we did is by defining and implementing some user-defined module. So as you can see here, that's MapleCar components, MapleCar user library. And we define various objects, say a body frame, brake system, control systems, drivers. And we also have some environments, and also have the powertrain, steering, suspension wheels, so all the subsystems you've already seen in the previous slides. So I'm going to give you a quick look about how this stuff should look like. So the way to use it is just like other components in the MapleSim library, just drag and drop. So this is the body frame components. So actually it's implemented using the Modelica language, so which has some interesting features. For example, you see by default the number of axles is set to be 2, right? But and look for this connection point here. It's supposed to be a standard vehicle with 2 axles, so you have 4 connection points for wheels and suspensions. So later on, if I switch to 3, so you will see the interface for extra connection point appears, right? And we can also do something like, say, if I want to have a trailer at the back, right? So I just click here, say I want a rear articulation. So you see, I want a rear articulation. You see the interconnection point just appears here, which allows user to later on to connect this vehicle to some trailer and do some configuration studies, right? So that's some features provided by the Modelica-based blocks. And this is some common parameter input blocks asked for the mass, velocities, inertia stuff. And here we have some sensing blocks to define, to ask the block to output some of the predefined measurements. For example, if I want to measure the speed, so I just click here. Oops, sorry. Let's remove this one. So I just click the speed, and you'll see the small triangle appears here and actually output the speed of the vehicle with the predefined measuring modules. And later on, we can attach a probe to it. So after forming the model, you should expect to see the plots of the velocity in the post-processing window, right? And also go to the simulation options panel. We have some predefined, diagnostic the models during runtime. So, for example, if we identify the vehicle has some roll issues or vehicle spins out, then we can either give some warnings or even stop the simulation. That's some built-in options. Built-in control of the simulation. And also we can either apply some aerodynamic drag forces onto the body frame, and we can do the trace, plot the CG trajectory during simulation. So that's for the frame module I'm going to briefly introduce. And we also have, I guess we should have a detailed look, for example, at here, this wheel module I've shown you in the slides. So here you see, by default, it's set to be linear type. So you see the, text and the icons here. And we have the, as I mentioned, so when, picking that specific subsystem, you don't need to worry the specific type to be used. They are going to be specified when you're going to do the vehicle modeling. So in this example, let's say I have the vehicle and I plan to have wheels, right? So I just drag and drop, and now I notice, okay, so instead of linear, I want a feeler type model. So I just switch the type, just like specifying the, the parameters. And you'll see the blocks, the tire property blocks here changes as I switch you see, as I switch the tire force model type. So these are some kind of type-specific parameters that we are going to collect from the user interface, right? So this is the longitudinal and lateral stiffness for the linear tire models, and this will be a full list of the other tire models parameters. Okay, so by having such components and stick with these ideas, so I've already did some predefined modeling by using these frame block, suspension blocks, and the field tire models along with the steering mechanism, and I apply a ramp steering to the vehicle systems. So I've solved the model, so let's switch to post-processing. So that's what that model looks like. So we have a traditional model with 2 axles and double wishbone suspension at both front and rear axles, and we also have a steering mechanism in front. So that's what the post-processing window looks like. And let's switch the view to top view and fix the camera to the CG of the vehicle. And you will see that the vehicle just goes straight, and when time goes to then the ramp steering applies, and you will expect to see the moving the steering mechanism and changing the vehicle orientation angles. So that's the first simulation example I would like to demonstrate. Hopefully you have a better idea about how this topology-based tool should look like and how it can be used for vehicle simulation. And this example, the second one, I'm going to show you how it can be easily extended to vehicle trailer configurations. This is sometimes tricky to be modeled in the traditional vehicle simulation tools. But in MapleSim, I'll say our MapleCar environment, it will be straightforward because you already have that front vehicle ready, as I mentioned, right? And then just by having that rear articulation point and then have another trailer module. Again, they're available from the toolbox. From the body frame, you can have a trailer module, specify number of axles, attach the suspension and wheels to it, and then specify the specific type for each subsystems and do the connections. So the full, vehicle trailer module should be modeled in that quick manner. And this is a simulation for that model. So I think I plot. This line shows the trajectory of the CG of the trailer vehicle, and you see the smooth moving of the vehicle. So hopefully, by these 2 simple examples, you have a better idea about how our package looks like and how it can be used to accelerate the modeling process of vehicle subsystems. And then we're going to switch back to the slides. So we start from here. So as you've already seen, we can do a simple 4-wheeled vehicle modeling via our interface, user interface in MapleCar. And we can even simplify the modeling by combining the suspension and tires, and we name it a corner module. So that's some kind of shortcut we provided to ease the modeling. And this, the other simulation study you've seen for that vehicle trailer example, right? So again, on the left side, we have used that shortcut for the corner module, and on the right hand side, we can even go fancier by combining the 2 corner modules, and we name it some axle modules. So even less connection and objects. So that's the simple simulation case study case. And then we go to this full vehicle example model. So on the right bottom part, you see the vehicle model we've already modeled. And then on the upper part, you see a way of incorporate more subsystems. Say we bring the driver into the picture. We ask the driver to track the vehicle on a given trajectory and also track the given speed. So the driver, as we analyzed at the very beginning, right? The driver will, some control logic is built in. The driver will control either the shift the gears, apply the gas or brakes to change the speed, and also to do the steering to to track the given trajectory. And the driver signals will be sent to the drive lines, to the brake systems, and the steering mechanisms. And the brake signals, applied by the driver, will bounce through the ABS controllers. So in this example, we try to show you a simple example of how the controllers can be easily integrated into this MapleCar package. So you see all these subsystems came into the picture, and their topology is somewhat fixed. So we can, just follow the same previous ideas. We can drag, drop, and components and do the connections, and the model should be ready to be solved. So here we show you some of the simulation results for the spin rate of the tires. You see, when ABS on is, when ABS off, so some of the wheels are locked, while it's on, so the wheels are just free to rotate. So that's the full vehicle example I would like to present. And by noticing that, it's still sometimes complicated or not so easy or intuitive to be modeled. So we came up with the idea that by fully using the topology relationship existing vehicle subsystems, we can use Maple Worksheet to work with the MapleSim environment to even simpler the modeling process. So this slide will show you how we are going to turn this complex vehicle simulation model into these simple ones. So I will have some animation on the right-hand side. So let's have a look. So basically, we do it via some Maple worksheets. So you see now the worksheet is being loaded. So we call it MapleCar vehicle assembly template. So basically, user need to specify the type, then load some of the data. Actually, this worksheet also provides access to some of the database or some source of the data in local drives. So in the example you saw here, we load some of the vehicle body data and even override some of them, right? And then when it goes to suspension, we have a specified worksheet for vehicle suspensions, because we notice for detailed vehicle suspension modeling, you will have to access a lot of data. All those hard points will be, some kind of complex to be identified and input into the input box. So we create such kind of worksheet to allow user to load the data and store them later on, and then they can edit and manipulate as they wish. So all this is possible by incorporating to bring the Maple worksheet into this page. And so you saw here, I've loaded some readouts, the data, and by clicking that calculate button, so we can even do some component level analysis even before the full vehicle simulation is being performed. So you see in that example, we solved for some spring ratio curves versus the suspension travel. So that's some benefits, again, can be, that's some of the benefits we can have by using these Maple worksheet assembly techniques. So as a quick summary, so basically we can have quick access to some local data, so we don't need to key in all the time, and we can even save them in some local file directories. And we can do some, we can also override some of them, right? And we are also able to do some component level, component level simulation, and with some built-in test rigs, we can see some of the characteristics of the suspensions or even other components even before the full vehicle model is composed. And then finally, you will see by clicking this button, so actually we are going to generate a Modelica-based model from this Maple worksheet and bring it back to the MapleSim environment. Okay, so in this way, so we greatly reduced the work to, model a full vehicle model like you see on the left upper screen, to a simple vehicle model just having 3 major blocks, which are the vehicle system itself, driver models, and the environment. Then by some top-level connections between these 3 major subsystems, so the vehicle simulation model is ready to go. So that's, again, by realizing and identifying the topology connections between the vehicle systems and using the Modelica language, so it will be possible to do some programming and, do all those works in the Maple worksheet, and finally enable us to do more efficient modeling of vehicle systems. Okay, so this will be the final example I demonstrate today. So maybe you will have questions like, okay, so I have a specific, user-defined components. So how it can be, incorporated and work with the proposed MapleCar package. So in this example, we try to demonstrate, how the user-defined modules can be worked with, say, a MapleCar package existing components. So here, what we modeled is a three-wheeled urban vehicle with camber and tilting control. So the abnormal thing of such vehicles is first, as you can easily see, it's three-wheeled vehicles. It's, not the standard configurations. And actually, they have some specific features building their either suspension or chassis systems, which enables them to either apply active camber or tilting control of the vehicles. So this is something not covered in the current, say, MapleCar libraries. So what we can do is, user can still use all those, those blocks and functionalities provided by the MapleSim, do all the details, modeling, even, multidiscipline, everything is fine, as long as the interface works, the interface works with existing MapleCar package. So the user-defined specific components can work with all other systems we already have in the MapleCar package and accelerate the vehicle modeling. So in this example, you see we reuse, for example, the environment module, the driver module, the driveline system, the brake system, and even all the wheel modules. So the only specific user-defined components goes to that chassis and suspension systems. So that means user can more focused on developing their own, say, specific components and analyze its dynamic or control purposes. But most of the reproduced work can be implemented in this shared platform to ease the formulation of the simulation model. Okay, so here you see the animation for that camber. You see the camber angle changes of the vehicle when it's trying to cornering. So that's the simulation. The last example I will try to demonstrate. So here comes the conclusion. So hopefully you've seen that topology-based approach could be a very effective and flexible method in vehicle modeling for research as well as practical engineering projects. And Modelica language has the features that we are looking for to support the development for the topology-based vehicle modeling for various disciplines in an integrated manner. And Maple, and along with MapleScene, provides a good platform to implement the idea of our MapleCar for vehicle modeling and simulation. And finally, through the examples, hopefully it shows that the complicated vehicle subsystems can be modeled using our proposed MapleCar package. So thank you for your attention, and just feel free to contact us. You can either, just feel free to contact us if you have comments, suggestions, or questions about the proposed package and the interface design. And you can either reach us via MapleSoft, or you can reach me via my personal email at chen.tang@uwaterloo.ca. And also, to access or have a try on this package, just feel free to contact MapleSoft guys, and I guess they will be glad to help you with installing those packages. Okay, thanks, Grant. I will give it back to you.
Thanks, Chen. Let me just get my screen up here for you all. So thanks a lot for that presentation. I just kind of wanted to follow up with a bit of an introduction to the tools that were used in this project. So MapleSim, it's our multi-domain tool for system-level modeling and simulation, and it allows you to quickly build models of complex dynamic systems by selecting and connecting components from a large library of pre-built components covering a variety of domains like mechanical, multi-body, control, thermal, and more. So we also offer specialized libraries for batteries, drive lines, transmissions, tires, and again, that list goes on too. important to note, though, that unlike traditional tools like Simulink, connections between components represent physical connections and not just signal flows in one direction. So this is acausal physical modeling, and it greatly simplifies the modeling task and dramatically reduces the complexity of the resulting block diagram, since your models actually look like what it is that you're trying to model. So Maple is our interactive environment for mathematical analysis and design exploration. And Maple allows you to go beyond simulation and get a deep insight into your designs. Over 5,000 mathematical functions are ready to tackle problems like parameter tuning, optimization, Monte Carlo analysis, sensitivity studies, and again, the list goes on. In addition, because at the core of Maple and the MapleSim is a powerful engine for symbolic computing. So you're able to extract all the system equations from your MapleSim model, compute Jacobians on them, and get analytical solutions for inverse kinematics and dynamics. The Maple document interface allows you to easily capture every step you take in this process, and the resulting interactive documents, they're easy to share, review, validate, and reuse through your product design or PLM system. They can even be shared on the central server and are fully interactive within a web browser. So you can kind of think of them like you're creating small apps or tools to be used in your PLM system. A full program language also allows you to script and automate analysis tasks, but also allows you to define custom modeling components from first principles, and you can just easily bring those into MapleSim as a custom component block. So in all, Maple provides you with it's a really powerful environment for your design exploration with the models you're making within MapleSim. And system-level models are an essential ingredient in verifying and validating a design. Simulation models can be deployed to a real-time environment, connected with controller and sensor hardware, and used for HIL testing or hardware-in-the-loop testing, operator training, and system tuning. So sort of unique to MapleSim is our ability to generate really fast simulation code, which gives a lot of flexibility to use high fidelity and detailed models and still meet those real-time constraints which many people need for HIL simulation. So they don't have to sacrifice model fidelity and use some sort of approximation. And the code can be generated in many different target environments, including, for Simulink or LabVIEW. The FMI industry standard opens up additional opportunities, so it can really be integrated with a wide variety of tools that might be in your tool chain. So Maple and MapleSim are really powerful tools, and they enable a model-driven innovation process in your engineering research work. In addition, MapleSoft has a lot of expertise in system-level modeling, design validation, and hardware-in-the-loop. We've worked with dozens of research teams and organizations around the world to help them take advantage of state-of-the-art techniques and tools to allow them to deal with the growing complexity and to succeed in their research goals. Our mission is to help you make your engineering projects succeed. They allow you to achieve more in less time, reduce project risk, and produce and share better results.